Well, hello everybody. Welcome. My name's Philip Brown. I got a pretty cool problem right here. I really like this one. It made me think. It was kind of cool. We're dealing with percentage of error, which isn't so difficult. There's a pretty simple formula to follow, but what's really kind of cool about this one is how the rounding rule is applied to this situation. So let's go ahead and get into it, shall we? So what we've got is we've got a circle, right? The radius has been rounded to 3 centimeters, but the rounding rule is that we have been rounded to the nearest half of a centimeter, and our job is to figure out what's the maximum percentage of error in the area of this circle, right? So our first job is going to be to figure out how big or small could the circle be, right? Since it's been estimated to 3 centimeters and we've rounded to the nearest half centimeter, well, it's going to have the situation that our lower bound is 2.75 centimeters. But that's not entirely obvious. So let's explore how rounding really works and why really quick, and then you can figure out the upper and lower bound pretty quickly on your own. So basically, usually we round to the nearest whole number, like so from 0 to 1, anything in between, we round to the nearest. So if it's 0.5 or more, we round up. If it's less than 0.5, we round down. The reason that is anything less than 0.5 is closer to 0. So that's why if it's to the left of this middle right here, we round down because it's closer that way. Whereas the other way is that if it's more than that midpoint, so it's 0.5 or more, it's closer to 1, so we round that way because it's the smallest error to round to the nearest endpoint, right? Now, the reason we round from the middle up is just convention. That's how we do it. It's easier that way because it's the same one way or another. So we just go ahead, and if it's exactly at the middle and the midpoint, we round up. So now in our situation, we have a number line 2.5 through 3.5, and the reason we did it this way is because we're rounding to the nearest half of a centimeter. So the places that we could round to, the endpoints of these little intervals would be 2.5, 3.0, or 3.5 centimeters, right? Now, to the right of the midpoint, we round up. To the left, we round down, right? So our midpoints would be here, 2.75 and 3.25. Those are exactly in the middle of each of these little intervals. So 2.75 or more, we would round up. 3.25 or more, we would round up. However, if you're to the left of those midpoints, so if you're less than 2.75, you go down. Less than 3.25, you go down. Now, in our situation, we've been rounded already to 3, but we don't know what the actual value is. But we do know that it's been rounded to 3, and we know how this rounding works now. So we would know that anything 2.75 or more would be rounded up, whereas if it was all the way up to 3.25, it's going to get rounded down. So our interval is going to be, our lower bound is going to be 2.75, our upper bound is 3.25. So if it was at 3.25 or more, it would have been rounded to 3.5, whereas if it was less than 2.75, it would be rounded down. So our interval is definitely in here. Lower bound over here, upper bound over here. So we know that the lower bound is 2.75. We know the upper bound is 3.25. So that's how our circles work. Anywhere from 2 3/4 of a centimeter of a radius up to 3 1/4 centimeters radius. So we have our 3 circles look like this, right? All right. So lower bound, the estimate, the upper bound, pi r squared, that's the formula for the area, right? So let's go ahead and just figure these things out, right? This is what we've got. We've got 2.75 squared pi. I usually like to do the calculations afterwards. So pi's, it's irrational, so you can't actually write it out. So I usually try to do anything with pi in a calculator as late as I can. So our formula for percentage of error is you take the difference of the estimate and the actual, and you divide by the actual. Thing is, this is the estimate, right? These are the actuals. So it doesn't really matter which order these are in because you're just going to take the difference, right? You're going to take the absolute value. So let's go ahead and plug those in right here, right? So we've got, actually, this is the actual minus the estimate divided by the actual, right? And when we simplify that, we get 19.008%. So rounded to 3 significant figures, that's 19.0%. So that's from the lower bound. Now on our upper bound, when we do that, we find that we have a 14.8% percentage of error. 14.8 is the percentage of error. And our original question is, what is the maximum right? So the maximum percentage of error would actually be on the lower bound, which is surprising to me. I would have guessed, if I had to, that it would be the upper bound, but it's actually the lower bound. So our answer is 19%. Hey, if you liked this, let me know how it went. Leave me a comment. Do all that cool stuff for YouTubers. And if you are a math teacher and you'd like to use this problem or other problems, check out my Substack. I do a weekly fun problem there, give you some stuff that you can use in your classroom so you can do fun problems with your students. You'd be surprised how many would get on board, especially if you just keep doing it for a couple of weeks. No pressure, just invitation. Check out my website on teachingmath.org. All kinds of goodies there for teachers. Teachers Pay Teachers website has all kinds of resources for you math teachers as well. In the meantime, hey, I hope you have a great day.